You are sitting somewhere that feels solid. The floor beneath you does not tremble, the walls do not drift, the air does not thin into absence. Your body feels anchored, positioned, surrounded by space that behaves exactly as it did yesterday. The chair supports your weight with the same faithful pressure. The light falls through the window at familiar angles. Everything appears stable, fixed, permanent. You assume the universe has edges you will never reach, distances too vast to cross, but still distances within something. You imagine space as a container, even if it is unimaginably large. You imagine expansion as growth into more room, like water filling a bathtub or air expanding into a balloon. You picture galaxies drifting apart inside a larger emptiness, moving through a pre-existing cosmic arena that was always there, waiting. But that is not what the equations describe. That is not what the observations reveal. According to the most precise measurements we have, confirmed by observations of distant supernovae, the cosmic microwave background radiation, baryon acoustic oscillations, and the large-scale structure of galaxy distribution, the universe is expanding, not like an explosion into pre-existing emptiness, not like debris flying outward into surrounding darkness, not like fragments scattered across a cosmic void. Space itself is stretching, and here is the contradiction that refuses resolution. If space is everything that exists physically, then there is no outside for it to expand into. There is no external vacuum waiting beyond the boundary, no surrounding void, no container, no arena, no stage upon which the cosmic drama unfolds. So what does it mean to say the universe is expanding? What does it mean to say it is expanding into nothing? And what is that nothing? This is not poetry, though it may sound like it. It is not metaphor, though language fails here. It is not mysticism, though it touches the limits of comprehension. It is a direct consequence of general relativity and the mathematical models that describe cosmic evolution. The expansion is measurable, the geometry is calculable, the acceleration is real. Every prediction these models make has been tested and confirmed with extraordinary precision, yet the implications are deeply unsettling. They challenge every intuition you have about the nature of reality. If space can grow without expanding into anything, then space is not what you think it is. And if space is not what you think it is, and then neither is distance, neither is separation, neither is location, neither is the stage on which your entire existence unfolds. The framework you use to make sense of where you are and what surrounds you, the most basic categories of experience, may be fundamentally inadequate. Tonight, you will follow this question to its edge, not to the edge of the universe, but to the edge of meaning itself, to the boundary where language breaks down and intuition fails, to the place where mathematics continues but comprehension falters. You will confront what it means for reality to be stranger than strangeness, deeper than depth, more fundamental than the foundations you thought were bedrock. The room that is not still. You look around and nothing appears to move. The chair does not slide away from you across an expanding floor. The ceiling does not rise. The distance between your hands when you hold them apart does not stretch. The walls maintain their positions. The objects on your desk remain exactly where you placed them. Everything feels motionless, frozen in space, obeying the laws of everyday physics. And yet, at the cosmological level, every cubic centimeter of space around you is expanding. right now, right here. The geometry of the universe is changing continuously, everywhere, including in this room. The metric tensor that defines distance is evolving forward in time according to the Friedman equations. Space is not static. It never was. The reason you do not notice is deceptively simple. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, all the fundamental interactions that bind matter together, overpower cosmic expansion locally. The electromagnetic bonds holding molecules together are vastly stronger than the expansion trying to pull them apart. The gravitational binding energy of your body, this room, the Earth, and the solar system, even the Milky Way galaxy, completely dominates over the extremely weak stretching of space at small scales. But the expansion is still there. It is not absent. It is overwhelmed. If you could somehow turn off all other forces, if you could isolate two particles and shield them from every interaction except cosmic expansion, you would see them drift apart, slowly, imperceptibly, but measurably. The space between them would grow. Not because they are moving through space, but because space itself is stretching. This reveals something profound about the nature of stability. What you experience as solid, fixed, permanent, the immobility of objects, the constancy of distances, the reliability of space, is not fundamental. It is negotiated. It is the result of forces in competition. Gravity and molecular bonds happen to win locally, so your chair stays put. But on larger scales, where gravity cannot hold structures together, expansion dominates. Stability, it turns out, is not a property of space itself. It is an emergent phenomenon, a temporary balance, a local victory in an ongoing cosmic struggle. This means that the stillness you feel is conditional. If the expansion accelerates enough, and current observations suggest it is accelerating, then eventually, on timescales trillions upon trillions of years in the future, even gravitationally bound structures might be tested. Not today, not for unimaginable ages. But the expansion never stops. It accumulates. And what holds together now does so because the forces binding it are stronger than the expansion trying to pull it apart. For now. You sit in a room that appears perfectly still, but you are sitting inside a dynamic geometry, a stretching fabric, a universe that has never stopped growing since it began. Stillness is an illusion created by forces strong enough to resist the tide, but the tide is always there, flowing beneath everything, waiting. The discovery that broke the static universe. For centuries, you might have assumed the universe was eternal and unchanging. Philosophers and astronomers looked at the night sky and saw constancy. The stars occupied fixed positions. The cosmos appeared timeless, infinite in extent and duration, neither beginning nor ending, neither growing nor shrinking. This seemed like the natural state of things. What else could the universe be but permanent? Even Albert Einstein, when he formulated general relativity in 1915, expected the universe to be static. His equations described how mass and energy curve space-time, how gravity emerges from geometry. But when he applied these equations to the entire universe, assuming it was homogeneous and isotropic on the largest scales, he found something disturbing. The solutions were not static. The universe wanted to either expand or contract. It refused to stay still. Einstein found this so counterintuitive that he modified his own equations. Though he added a cosmological constant, a term representing a kind of energy inherent to space itself, specifically calibrated to counteract gravitational collapse and force a static solution. He called it his biggest blunder, though history would prove the cosmological constant was not wrong, just misapplied. The universe was not static, it never had been. In the 1920s, Edwin Hubble measured the light from distant galaxies using the 100-inch telescope at Mount Wilson Observatory. He noticed something peculiar. The spectral lines of elements in those galaxies were shifted toward the red end of the spectrum. This redshift could be explained if the galaxies were moving away from us, and the farther a galaxy was, the greater its redshift. The more distant the galaxy, the faster it appeared to recede. This pattern, velocity proportional to distance, became known as Hubble's law. It revealed something irreversible. The universe was expanding, not from a center, not into a void, but everywhere, all at once. Every region of space was growing. Galaxies were not moving through space like cars on a highway. The space between them was stretching like dots on an inflating balloon. This discovery shattered the static cosmos. If the universe is expanding now, then it was smaller in the past. If you trace the expansion backward in time, distances shrink, galaxies converge, the universe becomes denser, hotter, more compressed. Eventually, you reach a point where all matter and energy were concentrated in an unimaginably small, hot, dense state. This moment, approximately 13.8 billion years ago, is what we call the Big Bang. The Big Bang was not an explosion in space. It was the beginning of space. It was the moment when expansion began. Before that moment, if before even makes sense, there was no space, no time, no distance, no duration. The universe was not born into a pre-existing void. The void itself, such as it was, came into existence with the universe. Hubble's discovery transformed cosmology from philosophical speculation into observational science. The universe was no longer eternal and unchanging. It had a history. It had been stretching ever since it began, and it has been stretching ever since, every second, everywhere, including in the space between your eyes and this page. The static universe died in the 1920s, killed by precise measurements of distant light. In its place arose a cosmos that was dynamic, evolving, and historical, a universe that has never stopped growing and shows no sign of stopping. Expansion is not an explosion. It is tempting to imagine the Big Bang as a detonation in pre-existing darkness. You picture a point in empty space erupting outward, flinging matter and energy into a surrounding void. Galaxies as shrapnel, expansion as the aftermath of cosmic violence, a fireball growing larger inside a container. But that picture is fundamentally misleading. It imports assumptions from everyday experience that do not apply to the cosmos. When a bomb explodes, it sends debris outward through pre-existing space. There is a center to the explosion, the point where the bomb was. There are edges to the expanding cloud of debris. There is a surrounding environment into which the explosion propagates. The Big Bang was not like this. There was no surrounding void. There was no pre-existing space. There was no center. The Big Bang did not happen at a location. It happened everywhere. Every point in space was part of the Big Bang. If you had existed 13.8 billion years ago, you would have been inside the Big Bang, no matter where you were. The expansion of the universe is not matter moving through space. It is space itself, stretching. Imagine a grid of coordinates painted on the fabric of space. As the universe expands, the grid squares grow larger. Objects attached to those grid points, galaxies for instance, move apart not because they are traveling through space, but because the space carrying them is expanding. The galaxies are not moving. The space between them is growing. This is why every observer, no matter where they are located, sees the same pattern. If you were in a galaxy billions of light years away, you would see distant galaxies receding from you in all directions, just as we do. There would be no direction you could point and say, "The Big Bang happened over there." Every location has an equal claim to being the center of expansion, which means there is no center at all. This symmetry, this uniformity, is built into the mathematics. The Friedman equations, derived from general relativity, assume the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, on large scales. These assumptions match observations remarkably well. The cosmic microwave background radiation is uniform to 1 part in 100,000. Galaxy distributions are uniform when averaged over scales of hundreds of millions of light years. The universe looks the same in every direction. This uniformity means expansion cannot have a center. If there were a center, the universe would look different depending on how far you were from it. But every observer sees themselves surrounded by expanding space. Every point can claim to be stationary, while everything else recedes. This is the profound implication of cosmological expansion. It does not happen from somewhere. It happens everywhere, simultaneously, without preference or privilege. The Big Bang was not an explosion in space. It was the expansion of space. It was not the beginning of motion through a void. It was the beginning of space itself. And that difference, subtle in words, radical in implications, changes everything about how you must understand the universe. The balloon analogy and its failure. You may have encountered the balloon analogy. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move away from each other. Every dot sees every other dot receding. There is no privileged center on the surface itself. The expansion is uniform. This analogy captures something important: the idea that expansion can be intrinsic to a space rather than motion through a larger space. The dots are not moving across the balloon surface. The surface itself is stretching, carrying the dots with it. Similarly, galaxies are not flying through space. Space is expanding, and galaxies are embedded in it like raisins in rising bread dough. But the analogy hides something crucial. The balloon expands into the surrounding room. There is a three-dimensional space, the air around the balloon, into which the two-dimensional surface expands. You can watch from outside. You can measure the balloon's radius as it grows. You can point to the center of the balloon, even though that center is not on the surface itself. The universe does not work this way. There is no higher dimensional room we can point to. There is no external vantage point from which to observe cosmic expansion. There is no outside in the conventional sense. The equations of general relativity describe expansion intrinsically without reference to any embedding space. Mathematically, this is expressed through the metric tensor, a mathematical object that defines distances within space-time itself. The metric evolves over time, according to the Friedman equations. This evolution is described entirely from within the universe, using only measurements made inside it. There is no need to reference anything external. The expansion is a change in the internal geometry of space-time. This is profoundly difficult to visualize because your brain evolved to navigate three-dimensional space embedded in a larger context. When you imagine expansion, you imagine it happening into something. But the universe is not embedded in anything. It is all there is. The expansion is not growth into a pre-existing volume. It is growth of the volume itself. The balloon analogy comforts you. It gives you a mental picture, a way to grasp the concept. But the mathematics removes that comfort. The universe is not like a balloon. It is like a balloon with no surrounding air, no room, no outside observer, no embedding space. It is a balloon that expands without expanding into anything. And that is a concept your spatial intuition is not equipped to handle, that because you have never encountered anything like it in everyday experience. The analogy helps, but it also misleads. It sneaks in the very thing you are trying to escape, the idea of expansion into a container. The universe is the container, and the container is growing, and there is nothing outside it for it to grow into. The analogy breaks down precisely where the strangeness begins. What nothing actually means. When physicists say the universe expands into nothing, they do not mean empty space. Empty space is still something. It has a geometry. It has quantum fields permeating it. It has measurable properties like energy density and curvature. You can assign coordinates to it. You can measure distances across it. Empty space is not nothing. It is a type of something, a physical entity with structure. The nothing beyond the universe, if beyond even makes sense, is different. It is not a vacuum. It is not darkness. It is not a region waiting to be filled. It is the absence of spatial relation entirely, not emptiness, non-existence of dimension, not a place, the absence of place. This is extraordinarily difficult to conceptualize because your mind has no category for it. When you try to imagine nothing, you imagine darkness, empty space, a void. But darkness is something you see when photons fail to reach your eyes. Empty space is something with coordinates and geometry. A void is a region defined by the absence of matter. These are all forms of something. True nothing, the nothing beyond the universe, is not a space that happens to be empty. It is not a container waiting for content. That it is the absence of the framework that makes space possible. It is not that there is no matter there. It is that there is no there at all. Distance does not exist. Direction does not exist. Dimension does not exist. This is what philosophers call a conceptual impossibility. Not impossible in the sense of violating physical law, but impossible in the sense of being fundamentally unthinkable. Your cognitive architecture requires spatial frameworks. You think in terms of objects in locations. When you try to think about the absence of location itself, your mind substitutes something else. It imagines darkness instead of non-space. It imagines emptiness instead of the absence of dimension. The mathematics does not have this problem. General relativity describes space-time as a manifold, a mathematical structure that exists in its own right, thus without needing to be embedded in anything larger. The manifold has an intrinsic geometry defined by the metric tensor. This geometry can evolve over time. It can expand. and it does not require any external space to expand into. So when you ask, what is the universe expanding into? The answer is not empty space, or a void, or darkness. The answer is that the question contains a hidden assumption that may be wrong. It assumes there must be something beyond, some container or arena. But if the universe is all of space, then beyond has no meaning. There is no beyond. Not in the sense that you cannot reach it, but in the sense that the concept itself does not apply. Nothing is not a place. It is not a state. It is not a condition. It is the absence of the categories that make places, states, and conditions possible. And that absence is what lies beyond the universe. If lies and beyond are even meaningful words in this context, which they may not be, which is precisely the problem. The geometry of curved space. General relativity tells you that space is not a rigid backdrop against which events unfold. It is a dynamic geometry shaped by mass and energy. Massive objects curve space-time around them. This curvature is what you experience as gravity. The Earth does not pull you toward its center through some mysterious force acting at a distance. Instead, the Earth's mass curves space-time, and you follow the straightest possible path, called the geodesic, through that curved geometry. Falling is not deviation from straight motion. Falling is straight motion through curved space-time. This insight revolutionized physics. Space is not passive. It is not inert. It is an active participant in physical phenomena. It can bend, it can ripple, it can stretch, it can carry energy. Gravitational waves, ripples in space-time itself, propagate at the speed of light, carrying information about violent cosmic events. When two black holes collide, they shake space-time like a drumhead. That shaking spreads outward. We have detected these waves. Space is not just a stage. It is part of the performance. The expansion of the universe is a change in this geometry over time. Specifically, it is an increase in the scale factor, a number that describes how distances change as the universe evolves. If you mark 2 points in space and wait, the proper distance between them will grow. Not because the points are moving through space, but because the metric defining distance is changing. The ruler itself is growing, and when the ruler grows, every measurement changes with it. This has profound implications. It means that distance is not absolute. It is not a fixed property of the universe. Two galaxies separated by 1 billion light-years today were separated by less in the past and will be separated by more in the future. The distance between them is a function of time. Space does not just contain objects. It evolves. It has a history. Moreover, the curvature of space on cosmological scales depends on the total energy density of the universe. If the density is above a critical value, space curves back on itself, forming a finite but unbounded geometry like the surface of a sphere. If the density is below the critical value, space has negative curvature, like the surface of a saddle, and may be infinite in extent. If the density equals the critical value, exactly, space is flat. Euclidean geometry holds on large scales. Current observations suggest the universe is very close to flat. The cosmic microwave background radiation shows patterns consistent with flat geometry to high precision. This flatness is itself puzzling because it requires the density to be finely tuned. Even a tiny deviation from the critical density early in cosmic history would have been amplified over time, leading to pronounced curvature today. The fact that we observe near flatness suggests either extraordinary fine-tuning or some mechanism, such as cosmic inflation, that drove the universe toward flatness. Space is not a fixed grid, it is a flexible, evolving geometry. It bends around mass, it ripples from acceleration, and it stretches as the universe expands. The stage on which your existence unfolds is not passive scenery. It is an active, dynamic, malleable structure, shaped by energy and evolving through time. The observable horizon. There is a limit to how far you can see, not because the universe ends at that limit, not because your telescopes are insufficiently powerful, but because light has had finite time to travel since the Big Bang. The observable universe is defined by a horizon, the farthest distance from which light has had time to reach us in the 13.8 billion years since the beginning. This horizon is not a physical boundary, it is an informational limit. Beyond it, there may be infinitely more space. There may be galaxies, stars, planets, perhaps even life and civilizations. But we cannot see them. Their light has not had time to traverse the expanding space between us. We are trapped within a bubble defined by the speed of light and cosmic history. And the rest, whatever it is, remains forever inaccessible to our instruments. The current observable universe extends roughly 46 billion light-years in all directions from Earth. You might expect the limit to be 13.8 billion light-years, the age of the universe times the speed of light, but the expansion of space complicates the calculation. Light that was emitted 13.8 billion years ago has traveled through expanding space. The source that emitted it has been carried away by expansion. So while the light has traveled for 13.8 billion years, the object that emitted it is now much farther away, roughly 46 billion light-years. Beyond this horizon, events are occurring right now that will never influence us. Stars are forming, galaxies are colliding, the supernovae are exploding, but their light will never reach us because space is expanding, and in some regions it is expanding faster than light can cross it. These regions are receding from us at superluminal velocities, not because they are moving through space faster than light, which would violate relativity, but because the space between us and them is stretching faster than light can traverse it. This creates a fundamental limit to knowledge. No matter how advanced your instruments become, no matter how long you wait, there are regions of the universe you will never observe. The information they contain is causally disconnected from you. They exist in a domain forever beyond your reach. And if dark energy continues to accelerate expansion, this observable horizon will eventually shrink. The galaxies currently visible will cross beyond it. Your descendants, trillions of years from now, will see a lonelier sky. You are confined within a cosmic bubble. Beyond it stretches a universe you cannot see, cannot probe, cannot know. It may be finite, it may be infinite. You may never find out. The observable universe is not the universe. It is merely the portion that is currently, or will ever be, accessible to observation. The rest is real. It exists, but it is hidden from you by the fundamental structure of space-time itself. Acceleration and dark energy. In 1998, two independent teams of astronomers studying distant Type 1, a supernovae, made a discovery that shocked the scientific community. They were measuring the expansion rate of the universe at different epochs by observing supernovae at various distances. The type 1. A supernovae are excellent standard candles. Their intrinsic brightness is known, so measuring their apparent brightness reveals their distance. The expectation was that cosmic expansion would be slowing down. Gravity, after all, is attractive. The mass and energy in the universe should be pulling everything back together, decelerating the expansion. The question was only how much the expansion was slowing. Would it eventually reverse, leading to a big crunch? Or would it continue forever, gradually decelerating but never quite stopping? But the observations revealed something completely unexpected. The distant supernovae were fainter than predicted. They were farther away than they should have been if expansion were decelerating. This meant the universe was not slowing down. It was speeding up. The expansion of the universe is accelerating. This discovery earned the Nobel Prize in Physics in 2011. It also created a profound mystery. What could possibly be driving galaxies apart faster over time? What force or energy could overcome gravity on cosmic scales and accelerate expansion? The answer, or at least the name we give to our ignorance, is dark energy. Dark energy appears to be a form of energy inherent to space itself, a kind of cosmological constant, much like the one Einstein added to his equations a century ago for the wrong reasons. Dark energy has negative pressure, while matter and radiation dilute as the universe expands. Dark energy maintains constant density. The more space there is, the more dark energy there appears to be. This creates a feedback loop. Expansion creates more space. More space means more dark energy. The more dark energy drives faster expansion. The process feeds itself. And current observations suggest dark energy constitutes about 68% of the total energy content of the universe. It dominates over both matter, 27%, and radiation, less than 0.01%. The universe is mostly made of something we do not understand. We do not know what dark energy is. We do not know why it exists. We do not know why its density has the value it does. If dark energy were slightly stronger, the universe would have expanded so quickly the galaxies could never have formed. If it were slightly weaker or absent, the universe might have recollapsed long ago. The value seems finely tuned for the existence of structure and perhaps life. Acceleration changes everything. It means the universe will expand forever, faster and faster. It means isolation is inevitable. It means the cosmos is fundamentally stranger than anyone imagined before 1998. And it means that the dominant component of reality is something we have barely begun to comprehend. The future of isolation. If acceleration continues, and all evidence suggests it will, the future of the universe is one of increasing isolation. The expansion driven by dark energy will eventually carry distant galaxies away from us faster than light. Not because they are violating special relativity by moving through space faster than light, but because the space between us and them is expanding faster than light can cross it. This is already happening to the most distant galaxies. Their recession velocities, calculated from their redshifts, exceed the speed of light. We can still see them because the light they emitted in the past is reaching us now, having been traveling through expanding space for billions of years. But light emitted from those galaxies today will never reach us. It will never cross the expanding gulf of space between us. Over timescales of trillions of years, this isolation will intensify. Galaxies currently visible will cross our cosmic horizon. The night sky will gradually grow darker. Stars in distant galaxies will vanish one by one, not because they are dying, but because their light can no longer reach us across accelerating space. Eventually, only the local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller galaxies, gravitationally bound together, will remain visible. Beyond this island, darkness. Future observers, if any exist, may see a lonely universe and conclude, incorrectly, that their galaxy group is all that exists. They will have no evidence of the vast cosmos beyond their horizon. The expansion will have hidden the truth. This creates a profound epistemological problem. How much of the universe is already hidden from us? How many regions have crossed beyond our horizon? How much structure and complexity exists in domains we can never observe? The universe may be far larger and more complex than we will ever know. Our cosmic bubble may be a tiny fraction of what exists. The universe is fragmenting into isolated domains. Your descendants, if humanity survives that long, will inhabit a cosmos that grows lonelier with each passing eon. They will see less. They will know less. The expansion that revealed the universe's dynamic nature to us will eventually hide that same truth from them. Knowledge itself is being eroded by the geometry of space-time and the end of causal contact. As expansion accelerates, regions of space lose causal contact. Causality, the principle that causes precede effects, and that information cannot travel faster than light, means there are limits to how far influence can extend. Events occurring beyond a certain distance can never affect you. Signals sent today will never arrive. Entire civilizations, if they exist, may already be unreachable forever. This is not merely a practical limitation. It is a fundamental feature of the cosmos. The accelerating expansion creates what is called an event horizon, a boundary beyond which events can never influence us, no matter how long we wait. This horizon is similar in some ways to the event horizon of a black hole, except it surrounds us rather than being localized at a point. The anything beyond this horizon is permanently disconnected from our future. If there are civilizations there, we will never communicate with them. If there are events there, we will never observe their consequences. If there are discoveries there, we will never learn of them. The universe is not just expanding, it is fracturing into causally isolated patches. This fragmentation has disturbing implications for knowledge. There may be answers to fundamental questions, answers that exist somewhere in the universe that we will never access because they lie beyond our causal horizon. There may be natural experiments occurring in distant regions that would settle debates in physics. There may be phenomena unlike anything in our observable universe. All of it is real. All of it exists, but it is forever beyond our reach. The universe is not just large, it is becoming uncrossable. Events are happening that will never affect you. Regions exist that you will never influence. The cosmos is fragmenting into isolated domains, each sealed off by the growth of space itself. Causality has limits, and those limits are shrinking, finite or infinite. You may assume the universe must either be finite or infinite in spatial extent. Surely it is one or the other. But both possibilities are profoundly unsettling, and observations have not yet determined which is true. If the universe is finite, it has a topology you cannot easily visualize. It might curve back on itself like the surface of a sphere, finite in extent but without boundary or edge. You could, in principle, travel in a straight line and eventually return to your starting point, having circumnavigated the universe. But this topology would exist in four-dimensional space-time, not in a way you can visualize in 3 dimensions. Alternatively, the universe might be infinite. Observations are consistent with this possibility. If space extends infinitely, in all directions, then expansion does not increase the total size of the universe, because infinity plus anything is still infinity. Instead, expansion increases the scale between points. The distance between any 2 galaxies grows, but the totality remains infinite. Infinity growing larger defies intuition. What does it mean for something boundless to expand? How can infinite space become more spacious? Yet mathematically, this is perfectly coherent. The scale factor increases, the metric evolves, distances grow. The fact that there are infinitely many distances does not prevent each individual distance from growing over time. If the universe is infinite, then there are infinitely many galaxies, infinitely many stars, infinitely many planets. And if the universe is both infinite and governed by finite physical laws, then everything that can happen does happen infinitely many times. There are infinitely many copies of you scattered across infinite space. This is not speculation. It is a direct consequence of combining infinity with quantum mechanics and finite initial conditions. Finite or infinite, the universe unsettles intuition. Finite space without boundary violates the expectation of edges. Infinite space expanding violates the expectation the growth requires something to grow into. Both possibilities are strange. The both are consistent with observations, and you may never know which is true. The absence of an edge. You search for an edge, a boundary where something ends and nothing begins. This is how containers work. This is how spaces work in everyday experience. A room has walls, a country has borders, a lake has shores. Everywhere you look, spaces have edges, but current cosmology offers no evidence of such a boundary in the universe. The cosmic microwave background is uniform in all directions. Galaxy distributions are statistically the same in every direction on large scales. There is no preferred direction, no axis, no orientation that would indicate an edge. The universe may be unbounded. Like the surface of a sphere, it could be finite, yet without edge. A sphere's surface has no boundary. You can travel along it indefinitely without encountering a wall or a cliff. Similarly, the universe might curve back on itself in a higher dimensional way, making it finite but unbounded. Alternatively, the universe may be infinite, in which case there is no edge because there is no end. You can travel in any direction forever and never reach a boundary because there is no boundary to reach. Infinity does not have edges, it simply continues. Either way, finite and curved, or infinite and flat, there is no cosmic cliff, no wall at the end of space, no place where you could stand and point beyond, saying that direction is outside the universe. Every direction you point is inside the universe. Every location you occupy is inside the universe. There is no outside to point toward. The absence of an edge removes the comfort of containment, You expect spaces to be contained within larger spaces, but the universe contains everything. It is not contained. It has no walls, because there is nothing outside for walls to separate it from. The universe is all of space, and all of space has no edge. Quantum fluctuations in the vacuum. Even in what you call empty space, quantum fields fluctuate. This is not metaphor. This is measured reality. The vacuum is not empty. It seethes with activity. Particles and antiparticles momentarily appear in pairs, borrow energy from the uncertainty principle, exist briefly, and annihilate back into nothingness. These virtual particles are real enough to produce measurable effects. The Casimir effect, for instance, arises from quantum fluctuations. Place two uncharged metal plates close together in a vacuum, and they attract each other. Why? Because the space between them can only support certain wavelengths of quantum fluctuations, while the space outside can support all wavelengths. The pressure from fluctuations outside exceeds the pressure between, and the plates are pushed together. The vacuum has structure, it exerts force. If space itself is expanding, these quantum fields stretch with it. Reality at its smallest scales participates in cosmic growth. Quantum fluctuations that were once microscopic may be stretched to macroscopic scales during periods of rapid expansion, such as cosmic inflation. These fluctuations, magnified by expansion, may have seeded the formation of galaxies. The largest structures in the universe may have originated from quantum uncertainty. This means nothingness, as physics defines it, is not passive, it is not inert, it is active, unstable, generative. The vacuum is a seething foam of quantum activity, and when the vacuum expands, it carries this activity with it. Expansion does not occur in empty space. It occurs in a quantum field configuration that has energy, structure, and dynamics. The vacuum is not nothing. The vacuum is a physical state, the lowest energy configuration of quantum fields, and that state participates in expansion. Reality, even at its most fundamental level, is dynamic. There is no stillness, even in emptiness. The vacuum fluctuates, and the fluctuations expand. Inflation and the multiverse. Hypothesis. In the earliest fraction of a second after the Big Bang, perhaps 10 to the power of minus 36 seconds, the universe may have undergone a period of exponential expansion called cosmic inflation. During this brief moment, the universe expanded by a factor of at least 10 to the power of 26, doubling in size every tiny fraction of a second. This rapid expansion solves several cosmological puzzles, including why the universe is so uniform and why it is so flat. Inflation is driven by a hypothetical field called the inflaton field, which exists in a high-energy state. When this field is in its excited state, it behaves like dark energy, driving exponential expansion. Eventually, the field decays to its lowest energy state, releasing its energy as particles and radiation. This decay is called reheating, and it produces the hot, dense state from which the universe evolved. But here is the strange implication. Some models of inflation suggest it never completely stops everywhere. In some regions, the inflaton field decays and inflation ends, creating what we call a universe. In other regions, inflation continues. And in those continuing regions, quantum fluctuations can create new regions where inflation ends, producing more universes. This process repeats indefinitely. This scenario is called eternal inflation. It produces a multiverse, a collection of separate regions, each with its own post-inflationary evolution, each potentially with different physical constants and laws. These regions are causally disconnected. They cannot communicate or interact. Each is its own universe, expanding internally, isolated from the others. If this hypothesis is correct, your universe, the region you observe, may be one bubble among countless others. Each bubble expands internally. Each has its own history. None expands into shared external space. Instead, they are embedded in an eternally inflating background. A metaspace that continues to produce new universes indefinitely. The multiverse hypothesis arises naturally from some inflationary models. It is not ad hoc speculation, but it is also extraordinarily difficult to test. If other universes are causally disconnected from ours, how could we ever detect them? The multiverse may be real, it may be the natural outcome of inflation, but we may never be able to prove it. The limits of language. You rely on words like space, nothing, expansion, outside, beyond, edge, container. These words evolved to describe everyday objects and places, rooms, boxes, landscapes, containers with contents, boundaries with sides. Your language is built from metaphors grounded in physical experience, but when applied to cosmology, these words mislead. They smuggle in assumptions that do not hold. When you say the universe expands, you imagine it growing into something. When you say it has no outside, you imagine void. When you try to picture infinity, you imagine vastness. But the universe is not growing into something. The void beyond is not darkness. Infinity is not just very large. The problem is not that you lack sufficient vocabulary. The problem is that your cognitive architecture is shaped by evolutionary pressures that favored navigating three-dimensional space, filled with medium-sized objects moving at moderate speeds. Your brain did not evolve to comprehend curved space-time, quantum fields, or metric tensors. Thus concepts lie outside the domain for which your intuition was optimized. Mathematics does not have this problem. Mathematical notation can describe curved manifolds, intrinsic geometries, and expanding metrics without reference to embedding spaces. The Friedman equations describe cosmic evolution precisely. The metric tensor encodes all information about distances and curvature. The mathematics is clear. It is language that struggles. This is why physicists often say, the mathematics is the reality, not because they believe numbers are more real than matter, but because the mathematical structure captures aspects of the universe the language cannot. You can write down a metric for a closed, finite, unbounded universe. You cannot easily visualize it. The equations are the description. The words are approximations. Your confusion when contemplating cosmic expansion may not reflect a flaw in physics. It may reflect a mismatch between the universe and the categories your brain uses to make sense of experience. The universe is not required to conform to your linguistic intuitions. It simply is what the mathematics describes. And the mathematics describes something stranger than everyday language can adequately express. Time as a dimension. The grows. Expansion is not just spatial. It is not merely that distances between galaxies increase. The evolution of the universe is inseparable from time. Space and time are unified in general relativity into a single structure, space-time. They are not separate entities. They are aspects of the same four-dimensional manifold. As space expands, the structure of space-time evolves. The metric tensor, the mathematical object describing distances in both space and time, changes over time. This evolution is not random. It follows the Einstein field equations, which relate the curvature of space-time to the distribution of mass and energy. In a sense, the universe is not only stretching outward, but unfolding forward. The future contains more space than the past. The cosmos generates new spatial extent as time progresses. This is not a metaphor. It is a description of how the scale factor evolves. At earlier times, the universe was smaller. At later times, it is larger. Time and expansion are intertwined. This means your experience of duration is cosmological. The passage of time is not separate from the growth of space. You exist in a four-dimensional manifold that is evolving. Every second, the future unfolds. Every moment, new intervals of space-time come into being. You are not just moving through time. You are participating in the creation of temporal extent, and time is not a backdrop against which events occur. It is part of the dynamic structure of the universe. As the universe expands spatially, it also progresses temporally. The two are aspects of the same process. You exist inside an evolving four-dimensional geometry, and that geometry is growing in both space and time. Entropy and the arrow of expansion. The expansion of the universe aligns with the increase of entropy. These two processes, cosmic expansion and thermodynamic evolution, are deeply connected, perhaps even inseparable. As space grows, matter thins, density decreases, temperature drops. Structures that rely on temperature gradients and energy flows eventually decay. The universe moves inexorably toward a state of maximum disorder. Entropy is a measure of disorder, but more precisely, it is a measure of the number of microscopic states consistent with macroscopic observations. High entropy means there are many ways the system could be arranged at the microscopic level while still looking the same macroscopically. Low entropy means there are few such arrangements. The second law of thermodynamics states that entropy always increases in isolated systems. The universe, being everything, is the ultimate isolated system. This increase in entropy defines the arrow of time, the reason you experience time as flowing from past to future. You remember the past because your brain stores low entropy records of previous states. You do not remember the future because high entropy states do not reliably predict low entropy states. Ice cubes melt, coffee cools, stars exhaust their fuel. These processes all increase entropy and all proceed in one direction. The direction of cosmic expansion mirrors the arrow of time. Both point toward greater disorder, greater dissipation, greater isolation. You experience time moving forward because the universe moves toward maximum entropy. Expansion is not separate from your perception of past and future. It defines it. The stretching of space, the cooling of the cosmic microwave background, the eventual dimming of stars, all these are thermodynamic processes embedded in the evolution of space-time itself. If the universe were static, thermodynamic equilibrium would eventually be reached. Temperatures would equalize, energy would distribute uniformly, nothing would happen anymore, because there would be no gradients to drive change. But expansion prevents equilibrium from being reached on cosmic scales. The universe continues to cool. Expansion creates space for entropy to increase indefinitely. There is always room for more disorder. You exist in a universe that is simultaneously expanding and decaying. These are not two separate processes. They are two aspects of the same cosmic evolution. Expansion creates the conditions for entropy to increase. Entropy increases by dispersing energy across growing space. And together, they define the arrow of time, the fundamental asymmetry that makes change possible and memory meaningful. Heat death and maximum emptiness. If expansion continues indefinitely, and current observations suggest it will, the universe may eventually approach a state called heat death. This is not a sudden catastrophe. It is a slow, the inexorable slide toward maximum entropy, maximum disorder, maximum uniformity. It is the state where no work can be extracted because there are no temperature gradients, no energy flows, no structures capable of performing computation or sustaining life. Stars will burn out. The longest-lived red dwarfs have lifespans of trillions of years, but eventually they will exhaust their fuel. No new stars will form because the gas needed for star formation will be dispersed too thinly by expansion. Galaxies will go dark. One by one, the lights will go out. Black holes will dominate for vast timescales. They will grow by accreting matter and merging with each other. But even black holes are not eternal. Through a quantum mechanical process called Hawking radiation, black holes slowly evaporate. The larger the black hole, the longer it takes. But given enough time, unimaginable spans of 10 to the power of 100 years or more, even supermassive black holes will radiate away their mass and disappear. After the black holes evaporate, what remains? Thin radiation, individual photons stretched by expansion to wavelengths larger than galaxies. Perhaps electrons and positrons, the less stable particles scattered across expanding space at densities approaching zero. The temperature of the universe will approach absolute zero. The cosmic microwave background, already at 2.7 Kelvin, will redshift indefinitely toward nothing. This is not dramatic destruction. It is dilution into near-nothingness. The universe will not end with a bang. It will fade into silence. Expansion will continue, but there will be nothing left to expand. Just space, stretching endlessly, containing almost nothing. The possibility of vacuum decay. Quantum field theory allows another possibility, more sudden and absolute than heat death. The vacuum state you inhabit, the lowest energy configuration of quantum fields, may not be the true lowest energy state. It may be what physicists call a false vacuum, a metastable state that appears stable but is not truly at minimum energy. If a lower energy vacuum state exists, quantum mechanics permits a transition. Somewhere in space, quantum fluctuations could nucleate a bubble of true vacuum. This bubble would expand at the speed of light. Inside the bubble, physical constants would be different. Particles would have different masses, forces would have different strengths. The laws of physics, as you know them, would be rewritten. This transition is called vacuum decay. It would be catastrophic. The atoms might not be stable in the new vacuum. Chemistry might not work. Stars might collapse or explode. Life certainly would be impossible, and there would be no warning. The bubble would propagate at light speed. You would not see it coming. Vacuum decay is speculative. It may never happen. But the fact that it is permitted by the equations is unsettling. The structure of reality itself could change. The laws you depend on could be rewritten, not gradually, instantly, and there is nothing you could do to prevent it. The illusion of centrality. You may feel located at a meaningful position. This feeling is ancient and persistent. For most of human history, people believed Earth was the center of the universe. Copernicus displaced Earth from the center. Galileo confirmed heliocentrism. But surely the sun is special? No, the sun is ordinary among billions of stars. Cosmology reveals no preferred center. Every observer sees expansion. Every point can consider itself stationary, while everything else recedes. The universe is isotropic from every location. The symmetry is elegant and destabilizing. There is no privileged vantage point. You occupy a position, but it is not the position. The universe does not revolve around you. Your location is as arbitrary as any other. Centrality is an illusion. There is no center to be central to. Horizons that shrink, relative to you. As dark energy accelerates expansion, your observable horizon does not grow indefinitely. Some regions are crossing beyond it permanently. Galaxies beyond a certain distance recede faster than light. Light they emit will never reach you. This creates a cosmic horizon that is, in effect, shrinking. Knowledge becomes constrained not by ignorance, but by geometry. The structure of space-time limits what can ever be known. The cosmos is larger than what is observable, and the gap between what exists and what can be observed is growing. Your descendants will see a lonelier sky. Expansion gives. Expansion takes away, and there is nothing you can do to prevent this loss of knowledge. The mathematics that demands it, the expansion of the universe, is not interpretation. It falls out of the Friedman equations derived from general relativity. When you assume homogeneity and isotropy, assumptions supported by observation, dynamic solutions are inevitable. Static universes are unstable. The mathematics does not merely allow expansion, it requires it under realistic conditions. A static universe is unphysical. The natural state of the cosmos is dynamic, and observations confirm this. The universe is dynamic because the equations governing it permit no other stable outcome. This is not interpretation, it is calculation, and the calculation is unambiguous. The question of absolute nothing. You attempt to imagine what lies beyond the universe, but what is nothing? Absolute nothing is not darkness or void. It is the absence of place itself, not emptiness, the non-existence of dimension, the absence of the framework that makes spatial relations possible. If space defines relation, near and far, here and there, then absolute nothing is the absence of relation. There is no where in absolute nothing. These concepts dissolve because they require a spatial framework. The question, what is beyond the universe, may be incoherent. Beyond implies spatial relationship, but if the universe is all of space, then beyond has no meaning. The question contains its own refutation. The fragility of physical law. Dark energy, inflation, vacuum states, quantum fluctuations, these reveal that the structure of reality is contingent. The laws you depend on may be emergent properties of deeper fields, and if the fields can change, the laws can change. The constants of nature appear fixed, but why do they have the values they do? They could be different. In other regions of the multiverse, they may be different. Physical law may be environmental, not fundamental. The laws of physics feel eternal. But stability is not necessity. Reality is more fragile than you think. The ground beneath is not bedrock. It is a configuration of fields that happens to be stable for now. in redshift as a time machine. When you observe distant galaxies, you are not seeing them as they are now. You are seeing them as they were billions of years ago. Light takes time to travel. The farther the galaxy, the longer its light has been traveling, and the further back in time you are looking. The universe is not just large in space, it is deep in time. The most distant galaxies visible today emitted their light when the universe was young. You are seeing them as they appeared when the cosmos was only a few 100 million years old. Primitive, irregular, rich in star formation, very different from the mature spiral galaxies nearby. The Hubble Deep Field images reveal thousands of galaxies in various stages of evolution, a cosmic archaeology preserved by the finite speed of light. Redshift quantifies this cosmic time machine, that as light travels through expanding space, its wavelength stretches. Blue light becomes green, green becomes red, red becomes infrared. The amount of redshift tells you how much the universe has expanded since the light was emitted, which tells you how long ago the light was emitted, which tells you how far back in time you are looking. This means telescopes are time machines. The James Webb Space Telescope, observing in the infrared, can detect galaxies with redshifts greater than 10. These galaxies existed when the universe was less than 500 million years old. You are not merely seeing distant objects. You are witnessing cosmic history. Every photon carries information about the state of the universe when it was emitted. You exist at a particular moment in cosmic history, but when you look outward, you look backward. The universe around you is a temporal gradient, older nearby and younger far away. You inhabit the present, but you observe the past. And the deeper you look, the further back you see until you reach the cosmic microwave background, the earliest light in the universe, emitted 380,000 years after the Big Bang. The cosmic microwave background as fossil light. The cosmic microwave background radiation is the oldest light in the universe. It fills all of space, coming from every direction, uniform to extraordinary precision. This radiation was emitted 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. Before that moment, the universe was opaque, a hot, dense plasma where photons scattered constantly of free electrons. When atoms formed, photons decoupled from matter. They began traveling through space, essentially unimpeded, carrying information about the state of the universe at that moment. Those photons have been traveling ever since, redshifted by expansion from visible light to microwaves. Today, they reach us from all directions, cooled to 2.7 Kelvin above absolute zero. The cosmic microwave background is a snapshot of the infant universe. Tiny temperature fluctuations, 1 part in 100,000, reveal the seeds of structure. Denser regions were slightly hotter. These regions eventually collapsed under gravity to form galaxies and galaxy clusters. The pattern of fluctuations encodes information about the geometry of space, the density of matter, and the physics of the early universe. Measuring the cosmic microwave background has confirmed key cosmological parameters. The universe is flat to within measurement error. It contains roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The age is 13.8 billion years. The expansion rate today, the Hubble constant, is approximately 70 kilometers per second per megaparsec. All of this from analyzing fossil light. When you tune a radio to static, a small fraction of that noise is the cosmic microwave background. You are detecting photons emitted before the first stars formed, before the first galaxies assembled, when the universe was a nearly uniform sea of hydrogen and helium. You are listening to the echo of creation itself. Dark matter, the invisible. Scaffolding. Most of the matter in the universe is invisible, not because it is far away or obscured, but because it does not interact with light. This substance, called dark matter, that constitutes roughly 85% of all matter. It does not emit radiation. It does not absorb radiation. It does not reflect radiation. It reveals itself only through gravitational effects. Galaxies rotate too fast. The stars at their edges move at speeds that should fling them into intergalactic space, given the visible mass. But they remain bound. Something unseen must be providing additional gravitational pull. That something is dark matter. It forms massive halos around galaxies, holding them together through gravity alone. Galaxy clusters also reveal dark matter. When astronomers measure their total mass by observing how they bend light from background galaxies, a phenomenon called gravitational lensing, they find far more mass than can be accounted for by visible matter. The dark matter outweighs the ordinary matter by a factor of 5 to 1. Dark matter may consist of exotic particles that interact only through gravity and possibly the weak nuclear force. Candidates include WIMPs, weakly interacting massive particles, or axions. Despite decades of searching, these particles have not been directly detected. Dark matter remains one of the greatest mysteries in physics. We know it exists. We know how much there is. We do not know what it is. Dark matter shaped cosmic structure. In the early universe, dark matter clumped first, creating gravitational wells into which ordinary matter fell. Galaxies formed inside dark matter halos. The large-scale structure of the cosmos, the cosmic web of filaments and voids, traces the distribution of dark matter. Visible matter is just foam on the surface of a dark ocean. You exist in a universe dominated by substances you cannot see. Dark matter outweighs ordinary matter. Dark energy dominates the total energy budget. Together, they constitute 95% of the universe. The atoms you are made of, the light you see, the familiar physics of chemistry and electricity, all of it is a small minority component in the cosmos dominated by darkness. The incomprehensible scale. The universe is larger than human comprehension. Numbers become abstract. Distances lose meaning. Your mind evolved to navigate terrestrial distances, measured in meters and kilometers, cannot grasp cosmic scales, measured in billions of light years. The Earth is tiny. Diameter, 12,700 kilometers. The Sun is larger. Diameter, 1.4 million kilometers. The distance from Earth to the Sun is 150 million kilometers, called 1 astronomical unit. This distance, sufficient to contain over 100 Earths laid side by side, is the basic unit for measuring the solar system. Neptune orbits at 30 astronomical units. The Kuiper belt extends to perhaps 50 astronomical units. The Oort cloud, a spherical shell of icy bodies surrounding the solar system, may extend 100,000 astronomical units, nearly 2 light years. Light from the Sun takes over a year to reach the Oort cloud's outer edge. The nearest star, Proxima Centauri, is 4.24 light-years away. Traveling at the speed of the fastest spacecraft ever built, it would take 80,000 years to reach. The Milky Way galaxy is 100,000 light-years across, containing 200 to 400 billion stars. Traveling at light speed, you would need 100,000 years to cross it. Andromeda, the nearest large galaxy, is 2.5 million light-years away. The local group of galaxies spans about 10 million light-years. The Virgo supercluster, which contains the local group, extends 110 million light-years, and the observable universe, the sphere within which light has had time to reach us, extends 46 billion light-years in every direction. These numbers are too large for intuition. You cannot visualize a billion light-years. You cannot hold it in your mind. The scale overwhelms comprehension, and yet this is merely the observable universe. Beyond it may be infinitely more. The totality is unimaginable. You exist on a mote, inside a galaxy among billions, in an observable patch that may be an infinitesimal fraction of the whole. Scale humbles. The universe is vast beyond imagining, and you occupy a position within it so small that on cosmic charts, your entire civilization would not be visible, not because you are far away, but because you are too small to register. The universe does not care about scale. It simply is what it is, unimaginably large, incomprehensibly vast, and expanding. Ripples in space-time, gravitational waves. Space is not merely a passive stage, it can vibrate. When massive objects accelerate, especially in violent events like black hole collisions or supernova explosions, they shake space-time itself. These ripples propagate outward at the speed of light. They are gravitational waves. Einstein predicted gravitational waves in 1916 as a consequence of general relativity, but they were not detected until 2015, a century later. The LIGO observatories, two L-shaped detectors, separated by thousands of kilometers, measured a gravitational wave produced by the merger of two black holes 1.3 billion light-years away. The ripple compressed and stretched space by less than the width of a proton over a distance of several kilometers. Detecting this required extraordinary precision. The instruments measured changes in distance smaller than an atomic nucleus. The signal was clear, a characteristic chirp as the black holes spiraled together, merged, and settled into a single black hole. This event released more energy in gravitational waves than all the stars in the observable universe emitting light combined. For a fraction of a second, the merger outshone everything. Gravitational waves confirm that space-time is dynamic. It is not rigid scaffolding. It bends around mass. It vibrates from acceleration. It carries energy, and it participates in physical processes. Space is not passive background. It is an active component of the cosmos, shaped by matter and energy, capable of transmitting information across the universe. You exist in a universe where space-time ripples. Right now, gravitational waves from distant cosmic events are passing through you, compressing and stretching space by imperceptible amounts. You do not feel them, but they are real. They confirm that space is physical, dynamic, and responsive. The fabric of reality vibrates, and we have learned to listen. The particle horizon and cosmic time. The observable universe is defined by a particle horizon, the maximum distance from which light has had time to reach us since the Big Bang. This horizon grows over time, but not without limit. Because space is expanding, and because expansion is accelerating, there are regions of the universe we will never observe, no matter how long we wait. The particle horizon is not a wall or a boundary, it is an informational limit. Beyond it lie events that have not yet had time to influence us. But crucially, due to accelerating expansion, some events that are beyond the horizon today will remain beyond it forever. The expansion of space prevents their light from ever reaching us. This creates a fundamental asymmetry in cosmic time. The past is accessible. You can observe it by looking at distant galaxies whose light left them billions of years ago. But the future is partially hidden. Events occurring now in distant regions may never influence you. They are causally disconnected. They exist in a domain forever beyond your reach. The particle horizon divides the universe into two domains: the observable, which is causally connected to you, and the unobservable, which is not. This division is fundamental. It is not a limitation of technology. It is a consequence of the structure of space-time itself. There are parts of the universe you will never know, not because you lack instruments, but because the geometry of space forbids it. The anthropic principle and fine-tuning. The constants of nature appear finely tuned for the existence of life. Change the strength of gravity slightly, and stars burn out too quickly or too slowly. Change the strength of electromagnetism, and atoms become unstable. Change the mass of the electron, and chemistry fails. The universe operates within a narrow range of parameters that permit complexity, structure, and ultimately, then observers like you. This observation leads to the anthropic principle. The universe must have properties compatible with the existence of observers, because if it did not, there would be no observers to notice. This may sound circular, but it has profound implications. If the multiverse hypothesis is correct, if there are countless universes with different physical constants, then only universes within the narrow range of life-permitting parameters will contain beings capable of asking why the constants have the values they do. Dark energy is a prime example. Its density appears finely tuned. If it were much larger, galaxies could never have formed. If it were negative, the universe would have recollapsed long ago. The value observed seems calibrated to allow billions of years of cosmic evolution, sufficient time for stars to form, heavy elements to be synthesized, planets to coalesce, and life to emerge. This does not prove the multiverse, but it suggests that the parameters of our universe may not be random. Either they are the result of a selection effect, we exist in a universe that permits our existence, or they are determined by deeper principles we do not yet understand. The fine-tuning is real. The explanation remains open. The formation of cosmic structure. The universe began nearly uniform. The cosmic microwave background reveals tiny fluctuations, 1 part in 100,000, but on large scales, the early universe was smooth. How did this smooth beginning give rise to the complex structure we see today? Galaxies, galaxy clusters, vast cosmic voids, filaments spanning hundreds of millions of light years? The answer lies in gravity. Tiny density fluctuations, preceded perhaps by quantum fluctuations during inflation, were amplified by gravitational instability. Denser regions attracted more matter. As they grew denser, they attracted more strongly. The feedback loop ensued. Over billions of years, these small perturbations grew into the galaxies and clusters we observe. Dark matter played a crucial role. Because dark matter does not interact with radiation, it began clumping earlier than ordinary matter, which was held in a hot plasma by radiation pressure. Dark matter formed gravitational wells. When the universe cooled enough for atoms to form, ordinary matter fell into these wells. Stars ignited, galaxies assembled, structure emerged from near uniformity. You exist inside a galaxy that formed through this process. The atoms you are made of were forged in stars, scattered by supernova, they're reassembled in molecular clouds, incorporated into planets. Your existence is cosmological. You are not separate from cosmic structure formation. You are its product. The universe organized itself, and you are part of that organization. The great voids between galaxies are not distributed uniformly. They cluster along filaments and walls, forming a cosmic web. Between these structures lie vast voids, regions hundreds of millions of light years across, nearly devoid of galaxies. These voids constitute most of the volume of space. They are not empty, they contain diffuse gas and dark matter, but they are profoundly underdense compared to galaxy clusters. The largest void discovered, the Boötes void, spans 330 million light years and contains very few galaxies. If you were in a galaxy inside such a void, the night sky would be nearly empty. No nearby galaxies, no local group, just vast darkness in all directions. The cosmic horizon might be the only source of distant light. Voids are not anomalies. They are the natural consequence of structure formation. Matter clumps, space empties, the cosmic web emerges. You happen to exist in a relatively dense region, near a spiral galaxy, within a galaxy cluster surrounded by structure, but most of space is void. Most of the universe is nearly empty, expanding between islands of matter. The ultimate fate of the cosmos. If dark energy continues to drive accelerating expansion, the universe will expand forever. Stars will exhaust their fuel. Galaxies will dim. Black holes will evaporate. Eventually, after timescales so vast, they dwarf the current age of the universe by factors of trillions upon trillions. The cosmos will approach maximum entropy. No stars, no galaxies, no black holes, just diffuse radiation and isolated particles separated by ever-growing distances, cooled to near absolute zero. This is called heat death, or the big freeze. It is not an explosion or a collapse. It is a slow fade into darkness and silence. The universe will not end. It will simply become empty, cold, and still. Expansion will continue, but there will be nothing left to expand between. Just space, stretching endlessly, containing almost nothing. Alternatively, if dark energy changes or new physics intervenes, other fates are possible. The Big Rip. If dark energy strengthens over time, it could eventually tear apart galaxies, stars, planets, atoms, even atomic nuclei. The Big Crunch. If dark energy reverses, expansion could stop and reverse, decollapsing the universe back into a hot, dense state. The Big Bounce. Some models suggest the universe could oscillate, collapsing and re-expanding indefinitely. We do not know which fate awaits. Current observations favor eternal expansion and heat death. But the universe has surprised us before. Dark energy was unexpected. Accelerating expansion was shocking. The future may hold revelations we cannot yet imagine. All we know is that the universe is not static. It evolves, and its ultimate fate remains uncertain. Philosophical implications of cosmic expansion. The expansion of the universe has philosophical implications that extend beyond physics. If the universe is expanding without expanding into anything, then the concept of absolute space, a fixed stage on which events occur, is incoherent. Space is not a container. It is a dynamic, evolving relationship between events. This challenges intuitions about existence. What does it mean to exist if the framework defining existence is itself changing? If distances are not fixed, if space itself grows, then what is the nature of location? Where are you, exactly? If the answer changes over time, not because you move, but because space stretches. The finite age of the universe raises questions about causation and existence. If the Big Bang was the beginning of time, what does before mean? Can there be causation without temporal precedence? Does asking what came before time even make sense? These are not merely scientific questions. They touch on metaphysics, the nature of reality, the limits of comprehension. You exist in a universe that defies common sense. Space is not what you think. Time is not what you assumed. The framework of existence is dynamic, contingent, stranger than imagination. Philosophy must grapple with this strangeness. Reality is not obligated to conform to human intuition. It simply is what it is. You inside the expanding fabric. You are composed of atoms forged in ancient stars, scattered across space by supernovae, gathered by gravity into molecular clouds, condensed into a solar system, assembled into a planet, organized by chemistry and evolution into a living organism. Every atom in your body has a history that extends billions of years into the past. You are made of stellar ash. You are a temporary configuration of matter that has been recycled countless times through the cosmic furnace. And you are embedded in a galaxy, drifting through expanding space-time. The Milky Way is gravitationally bound, so it does not participate in cosmic expansion. The stars around you maintain their relative positions. The spiral arms persist, but beyond the local group, the cluster of galaxies that includes the Milky Way and Andromeda, distant galaxies recede, horizons grow, causal domains fragment, and yet you sit here feeling stationary. You do not feel the expansion. You do not sense the geometry of space-time evolving beneath you. The distances between your cells remain stable, held together by electromagnetic forces. The distance from your hand to this page does not grow. Local physics dominates, but the expansion is still there, overwhelmed but present, waiting in the fabric of space. The universe does not expand away from you, as if you were at a special location. It expands through you. The metric tensor that defines distance between your cells is the same tensor that defines distance between galaxies. You are part of the expanding geometry, not separate from it. You are inside the process, not watching it from outside. This means your existence is cosmological. You are not a spectator observing the universe from a detached vantage point. You are woven into its fabric. Your atoms are participants in cosmic history. The space you occupy is part of the expanding manifold. The time you experience is part of the evolution of space-time. You are inside the universe, looking at the universe. You are the universe examining itself. And this raises a final, unsettling question. If the universe is expanding into nothing, and you are inside the universe, then what are you inside of? the answer is both simple and incomprehensible. You are inside of space, and space is inside of nothing, which means you are embedded in a geometry that exists without external support, without embedding, without a container. You are floating in a manifold that curves back on itself or extends infinitely, held together by its own internal structure, expanding for reasons still not fully understood. You look around at the walls, the floor, the ceiling. You feel anchored, you feel located, but you are situated in a universe that has no absolute location, no fixed position, no center, no edge, no outside. You are somewhere inside an expanding geometry that is everywhere and nowhere, finite or infinite, bounded or unbounded, growing without growing into anything. This is the final realization. You are not watching expansion happen. You are participating in it. Every second, the fabric of space-time evolves. Every moment, the geometry changes. The universe is not a static stage on which events occur. It is a dynamic, evolving process. And you, your thoughts, your existence, your experience of this moment are part of that process. You are inside the expanding fabric, and the fabric is all there is. There is no outside, there is no beyond. There is only the manifold, stretching, evolving, carrying you forward through time. You are cosmological. You are inseparable from the universe. You are expansion itself, briefly organized into awareness, contemplating its own nature. Coda, the edge of meaning. You have followed this meditation to its conclusion. You have confronted the idea that space can expand without expanding into anything, that the universe has no outside. That expansion is not motion through a void, but growth of the void itself, that you exist inside a dynamic geometry with no external support, no embedding, no container. These are not poetic metaphors. They are mathematical facts, confirmed by observation, derived from the most successful physical theory ever constructed. General relativity describes a universe that is stranger than fiction, deeper than myth, more alien than imagination. And you live in it. What you feel when you contemplate this, the vertigo, the confusion, the sense that language is failing, is appropriate. You are at the edge of what human cognition can grasp. Your brain evolved to navigate three-dimensional space filled with objects. It did not evolve to comprehend a four-dimensional manifold with intrinsic curvature expanding without external reference. Then the fact that you find this difficult is not a failure. It is recognition of genuine strangeness. But you now know something profound. You know that stability is not fundamental. You know that space is dynamic. You know that expansion is real, measurable, accelerating. You know that the universe has no center, no edge, no outside. You know that you exist inside a geometry that is all there is. And perhaps most importantly, you know that reality is not required to conform to your intuitions. The universe is not obligated to make sense in terms you find comfortable. It simply is what it is. And what it is, a curved, expanding, evolving space-time manifold without external embedding, is stranger and more beautiful than anything your ancestors could have imagined. You sit in a room that feels still, but beneath that stillness, space is stretching, galaxies are receding, horizons are shrinking, entropy is increasing, and you are part of it all, embedded in the fabric, participating in the expansion, existing inside a universe that expands into nothing because there is nothing beyond it to expand into. This is the edge of meaning, not because meaning ends here, but because language struggles to keep pace with mathematics. The equations continue where words falter. The universe persists where comprehension wavers. And you, for this brief moment, have glimpsed the profound strangeness at the heart of existence. The room around you has not changed, but your understanding of it has. You now know what you are sitting inside. You now know what it means to exist inside expanding space. You now know that the floor beneath you, solid as it feels, is part of a dynamic geometry that has been growing for 13.8 billion years and will continue growing forever, carrying you forward through a cosmos that is vaster, stranger, and more fundamentally mysterious than any human thought could fully contain.